Ladies and gentlemen, welcome. This is our seminar number 11 of 4ST601, Statistics in English. And if you remember, last seminar, last week, we finished here in the case of this example where we have two independent statistical samples, large samples because n, the sample size, in all cases, both cases, is higher than 30 observations. Yes, we have 32 males, 52 females, so two samples. And using the data in this table, we will determine with 95 and 99% confidence level the intervals of average number of achieved points of students from the midterm test of statistics. At the end of last seminar, we calculated two sample means, two sample averages for females and males, and two sample standard deviations for females and for males. Because there is no mention about the distribution, as we must use the general distribution in population. So please check your formulas, find this confidence interval about general distribution in population. Variance is unknown but finite. Yes, we know, we already estimated the deviation. The second power of deviation is the variance. Large sample, n must be higher than 30, and there is formula for two-sided confidence interval for parameter Ex, expected value. So I will rewrite this formula on the whiteboard. I will also rewrite the sample statistics, and we will solve two confidence intervals for males and for females. Because we require 95 and 99% confidence level. So the general confidence level, what was here? X with stripe minus Z1 minus alpha divided by 2 times standard deviation divided by square root from the sample size. And the right side, X with stripe plus Z1 minus alpha divided by 2 times standard deviation divided by square root from n. Okay, so very important that n1 is equal to 52, n2 is equal to 32. The mean for females and the mean for males. Yes, I will check the screen. 16.058, 16.058, and here 15.719. 15.719. Okay, and deviation 1, deviation 2. Okay, so 3.797, 3.797, and here 3.228, 3.228. Okay, so if we require 1 minus alpha equal to 0.95, yes, we know that alpha must be equal to 0.05, and therefore we are searching for quantile Z 0.975, 97.5% quantile of the standard normal distribution, yes? And I said on the previous seminar that it will be good for you if you remember the value of this very important quantile, yes? Z 0.975. If we require significance or confidence level 99%, yes, 0.99, alpha is equal to 0.01, yes, and therefore there will be 1 minus 0.01 divided by 2 is Z 0.995, yes. So please check your own statistical tables, yes. Maybe somebody from you remember from the previous week that we already found this quantile, yes. Its size is 2 point something, yes, something higher than 2. I don't remember, yes, this quantile, so I will check the screen, yes, and I will find this quantile for you. So please, you can verify 2.576, yes, 2.576. Check your tables and find and verify that you are able to find these quantiles, yes. So I will write here Z 0.975 equal to 1.96, yes, and Z 0.995 equal to 2.576, yes. So we know where we found everything, yes, and now we will solve these intervals. So we will start, for example, with females, yes. Okay, with females. 95 and 99% confidence level. So I will start 16.058 minus 1.96 times deviation 3.797 divided by square root from 52. Yeah, so this is the left side and right side. 16.058 plus 1.96 times deviation 3.797 divided by square root from 52. Yeah, so this will be the first confidence interval. The second one will be written, for example, here. So again, x1 mean 16.058. 16.058 minus another quantile, yes, 2.576 times 3.797 divided by square root from 52, and there will be 16.058 plus 2.576 times 3.797 divided by square root from 52. Yes, so I will use the calculator and I will calculate this ratio, yes, somewhere, because this ratio is still the same, and this name, yes, of this ratio is sample error in literature, yes. Maybe Mr. Hellman used something different, but sample, yes, error can be called this ratio, yes, sample error. So I will solve this. 3.797 divided by square root from 52, enter 0.527. 0.527, yes? So if we know that this is sample error, yes, so we can write everywhere quantile times sample error, yes, and here as well sample error, sample error, okay, and here as well sample error, yes, and here as well sample error, yes, so times sample error. It's very easy, ratio, yes, deviation divided by square root from n, yes, it's the same in all cases. And now we will solve this. So the left side, yes, sample error 0.527 times 1.96, and now 16.058 minus this value 15.03, for example, yes, only because I need a space here. And the right side 0.527 times 1.96 plus 16.058, 17.09, 17.09, yes, the left bound, right bound, yes, 95% confidence level. Okay, so again, sample error 0.527 times 2.576. Okay, 16.058 minus this value, left side, 14.70, 14.70. So this is the left bound, yes, left side of this confidence interval, and right side 0.527 times 2.576 plus 16.058, 17.42, 17.42, yes. You can see that on the basis of the same data set, yes, confidence interval with 99% confidence level, yes, is wider than if we use 95% confidence level, yes, and the same will be done for males, yes. So we know quantiles, I don't need deviation for females anymore, I don't need mean for females anymore, and I don't need this sample size, yes. Okay, so this will be deleted, and we will start with calculation. We will start with calculation of sample error, yes. So males sample error, yes, is deviation divided by square root from n. In our situation, 3.228 divided by square root from 32, yes, and there will be calculated this sample error 3.228 divided by square root from 32 males 0.571, okay, 0.571. Okay, and now the mean for males 15.7 719 minus 1.96 times sample error, yes, sample error. So this is the left side, right side 15.719 plus 1.96 times sample error. Okay, so I will solve this. So there will be left bound, there will be right bound, yes, and this will be deleted, yes, because this is for females. Okay, so I'm ready, and now 0.571 times 1.96, 15.719 minus this result, 14.60 points, yes, and the right side 0.571 times 1.96 plus 15.719, 16.84, 16.84. So this is 95% confidence level and 99% confidence level must be wider, yes, than this one. So the left side will be, I don't know, 14.1, and the right side, for example, 17.2. I don't know, I will calculate it, yes. So there will be 15.719 minus 2.576 times standard sample error, yes, and the right side 15.719 plus 2.576 times sample error. Okay, so left side, right side, yes, and 0.571 times 2.576, 15.719 minus this result, 14.25. 14.25, yes, you can see you are far away on the left side, here you will be far away on the right side, yes, so 0.571 times 2.576 plus 15.719, 17.19, 17.19 points, yes, so this is 99% confidence level, yes, with 99% probability we can expect, yes, that average number of points, yes, from the midterm test, if you are male, yes, will be between 14.25 points and 17.19 points, yeah? This is the interpretation. And the same with 95%, yes? You have 95% probability that if you are male, yes, your expected value, expected number of points from the midterm test will be between 14.6 points and 16.84 points. Yeah? So this is the interpretation and our last confidence intervals. We can fluently continue with hypothesis testing. So I've prepared this example for you. The brewery repaired quality of filling line for beer bottles. After repair, there were performed 21 measurements of bottles by random sample, yes. The average volume of the filled bottle was calculated, yes, on the basis of sample 500.76 milliliters of beer with a standard deviation 1.78 milliliter of beer. So that is written in the parenthesis that the values were calculated from the sample, from your selection of 21 bottles from the warehouse. Yes, we assume the normal distribution, and we would like to verify at a significance level alpha. Today we will start using this name, significance level, alpha equal to 0.05. That the repair was successful. It means we would like to verify whether the line fills the bottles of beers by volume of 500 milliliters. In other words, we want to verify whether the calculated average is significantly different from the required value of 500 milliliters of beer. On the whiteboard, yes, I will show you the story, illustrated story, how we obtain these values, yes, and after we will write the null and alternative hypothesis. We will select appropriate test statistic and the critical value. And after we will solve this B. So remember, please, this duty, how the process and the result changes. If the standard deviation of the filling volume is known, it means that this is not the value calculated from the sample, and its value is 0.78. So again, like in the case of confidence intervals, yes, we have two different situations. Yes, the first situation is that we know the variability of the population. Yes, so sigma is known. And the second case is that we don't know the variability in the population. So sigma or sigma squared is unknown. Yes, if we don't know the variance of the population, we must calculate, according to some formula, yes, the variability from the sample only. Yes, and from the previous seminar, you remember that calculation of variance or standard deviation from the sample only, using in denominator n-1, yes, n-1, because of compatibility with student t distribution. Yes, do you remember this? So two different situations, sigma known and sigma unknown. Yes, okay, so we will check the formula. So please wait a second. There is our formula for the last confidence interval, which we already solved, and I will scroll down where you can find statistical inference, statistical hypothesis tests. Yes, and there we can start. Yes, statistical hypothesis test for population parameters. We will start with parameters tests. So you can see that we have here a table divided to two parts. Yes, and as I already said, yes, there you can find sigma square known and the sigma square unknown. Yes, and in our example was written that the sample characteristic, sample mean and sample standard deviation, yes, were calculated on the basis of our sample, 21 bottles selected from the warehouse. Yes, so please make sure that you have ready this table with formulas in front of you. I will use the whiteboard and I will solve everything on the whiteboard. Okay, so the story, yes, there was a reparation of a filling line of beer bottles, yes, so you made a population of bottles, yes, and these bottles are in the warehouse, yes, and you walk through the warehouse, and from these bottles, population of bottles, you selected n equal to 21. Yes? So this is your sample size. So you have here bottles which you opened, for example, yes, and you measured, yes, the volume of these bottles. So you have a measurement units, values, yes, of observed variable, yes, the volume of beer. So x1, x2, x3 until x21, yes, 21 bottles. And on the basis of this mean, x with stripe is equal to summation through all e, xe divided by n. This is classical arithmetical mean. And according to this standard deviation, s is equal to square root from summation through all e, xe minus this mean, squared, divided by n minus 1. This is very important, yes? This is very important. So we have calculated a sample statistics, yes? We have calculated a sample mean equal to 500.36 milliliters of beer, yes? And we have calculated sample standard deviation 1.78 milliliters of beer, yes? How we calculate this mean? For example, this bottle, yes, has 501 milliliter, another bottle, yes, has 499 milliliters, etc. Yes, and everything was divided by 21. Yes, this is our sample statistic. But in case of deviation, there must be calculated n minus 1. Yes, but somebody calculated these sample statistics for you. Yes, so we will use this and we will continue. If you have opened these formulas, yes, in front of you, so there you have written 0 and alternative hypothesis. 0 hypothesis is every time only 1. In our situation, mu is equal to mu 0. What is it? Average volume, yes, of bottles will be equal to 500 milliliters of beer. Why? Because in the Czech Republic, yes, our bottle is half of liter. Yes. In Belgium, Netherlands, France, etc., using 330 milliliters. Yes. In Italy, 330, 500 and 600. Yes. So there are different sizes, yes, of the bottles in the world. Yes. But in the Czech Republic, the main standard, yes, is 500 milliliters. So we will verify if average volume of a bottle is equal to 500 milliliters of beer, yes. So this is our 0 hypothesis, yes. And if you check the formulas, you can see that we have here 3 types of alternatives, yes. Alternative hypothesis claims that mu is higher than mu 0. Another alternative hypothesis, mu is smaller than mu 0, yes. And the last one, which is here, mu is not equal to mu 0. Okay, so the first one, average will be higher than 500 milliliters of beer. This will be wrong for you, like owners of the brewery, yes, because you will give more beer to your customers for the same price, yes. So this is not correct. Mu will be smaller than mu 0, yes. You will put less beer to the bottles, yes. so your customers will be disappointed because they will receive less beer, yes, than 1/2 liter, so they will be sad and disappointed. So this is also wrong. So we will set alternative hypothesis that mu is not equal to mu0 because we require 500 milliliters, and wrong is if this is smaller or higher. Yes, both situations are wrong for you, like owner of brewery, and also for your customers. Yes, so this alternative hypothesis will be selected logically. Yes, so alternative 1, mu is not equal to 500 milliliters of beer. Yes, so this is the best alternative hypothesis which I selected. Okay, so I will delete this, and now important information about the variability of the population. As I already said, yes, sigma squared or sigma, yes, of population is unknown. Yes, sigma squared is unknown of the population. Therefore, we had to calculate this sample standard deviation. As if we calculate the second power of this value, we have a sample variance. Yes, but we don't need the sample variance, because if you check the formulas, yes, we need the deviation. So we will use test statistic with t distribution, because sigma squared is unknown, and this t statistic is calculated according to this formula. Calculated sample mean minus mu0 divided by standard deviation times square root from the sample size. Yes? So, because we know everything, absolutely everything, we are able to calculate this value of t-test, t-statistic, test statistic, test criterion, etc. So, calculated mean 500.36 minus the value which is set in the case of zero hypothesis, 500, divided by standard deviation 1.78. This is multiplied by square root from your random walk through the warehouse. Yes, so there is square root from 21 bottles. Yes, so the value of t statistic, the value of t test will be equal to, there is 0.36 in denominator divided by 1.78 times square root from 21. 0.927. 0.927. Okay, so this is the value of the test statistic, and now it's very important to say that this test statistic, test criteria, test statistic using Mr. Hellman, yes, test statistic in general, yes, can be element either of the region of acceptance V or rejection region W. Yes, region of acceptance or rejection region. The rejection region is more interesting for us, and this is the reason why we have written these rejection regions in our formulas. Yes, so you have here 3 rejection regions because we have 3 alternative hypotheses. Yes, first rejection region for the first alternative, second rejection region for the second alternative, and because this is third alternative hypothesis, we will select the third rejection region. Yes, so it will be good to check the rejection region and write it on the whiteboard. Yes, so please, I will create a space here. Yes, and from the screen I will rewrite the rejection region W alpha. W alpha is equal to, for the case of T statistic, is valid. Yes, if absolute value of your t-test is higher or equal to critical quantile t 1 minus alpha divided by 2, we entered to the rejection region and the zero hypothesis will be rejected at the particular level of significance. Maybe I will write this a little bit simplified for you. Yes, so W alpha is equal to, if absolute value of your t-test, this one, is higher or equal to critical value t critical, yes, from the tables, we entered to the rejection region and zero hypothesis is rejected at a significance level alpha. We must know that alpha is equal to 0.05. It was written in our example, yes? Test at the 5% significance level. Because alpha is 5%, we must identify this critical value from the tables. Yes, so t 1 minus alpha divided by 2 will be t 0.975. Yes, 5% divided by 2 is 2.5%. 100% minus 2.5% is 0.975. Yes, 0.975. So we will check the statistical tables, yes, and we will find this critical quantile with degrees of freedom, which is denoted by a small Greek letter ni, and this ni is equal to n minus 1. Yes, in our situation, n is 21 bottles minus 1, so this will be equal to 20 degrees of freedom. Yes, 20 degrees of freedom. So I will use the screen. Yes, we will find this quantile and I will recapitulate from the formulas what is written on the whiteboard. So one more time, I will start here at the beginning. I selected zero hypothesis because there is only one zero hypothesis. We have here three alternatives and our decision was that we will select the third alternative hypothesis because it's wrong if you have more beer in the bottle, and also is wrong if you have less beer in the bottle. Yes? And because our variance of the population is unknown, we must use this t-test, this test statistic with t distribution, mean minus mu0 divided by deviation times square root from the sample size. Yes? So we calculated the value of the test statistic, and there you can find three rejection regions. Yes, you can see first one, second one, third one. For the first alternative hypothesis, second alternative hypothesis, and the third alternative hypothesis. So because we selected third alternative hypothesis, I also selected this third rejection region where you can find absolute value of t statistic is higher or equal to t 1 minus alpha divided by 2, where alpha is significance level, and this t 1 minus alpha divided by 2 is critical value from the statistical tables of the student t distribution with degrees of freedom ni, and this ni is calculated like n minus 1. In our situation, 21 bottles minus 1 is equal to 20. So we will find critical value and we will compare absolute value of t statistic with critical quantile. In case that absolute value of your test statistic is higher than critical value, you entered to the rejection region and zero hypothesis is rejected at the particular level of significance. So the tables, statistical tables are here. I have here standard normal distribution, so I must scroll down. And there you can find quantiles of the student distribution TP. P value 0.975 is in the middle, and you can see the degrees of freedom are here. And we need 20 degrees of freedom and the column in the middle. So please find critical value 2.086. Yeah, so I will write this value on the whiteboard and we will decide. Okay, so critical value in our situation is 2.086. Yes. So now there is a question if absolute value of this test statistic is higher or equal to 2.086. No, yes, this is not true. So test statistic is not element of the rejection region. Because the test statistic is not element of the rejection region at the 5% significance level, H0 is not rejected. At the 5% significance level, zero hypothesis is not rejected. It means that average volume of beer, yes, in the beer bottles, is equal to 500 milliliters. In other words, it means that the reparation of the filling line was successful. Yes, there was a question or duty verify at a significance level alpha 5%. Then the repair was successful. It means verify whether the line fills the bottles of beer by a volume of 500 milliliters of beer. Yes, it is true because on the basis of our data set, the zero hypothesis was not rejected. Yes. And we will continue how the process and the result changes if the standard deviation of the filling line, of the filling volume is known. Yes, so it's not calculated on the basis of sample, and its value is 0.78. So very important now is that sigma, yes, of the population is known. So if you remember at the beginning I wrote here n as the population. I don't know how many, it's not written in the example. Yes, you made, for example, 20,000 of bottles. Yes, you selected in the warehouse n equal to 21 as this sample size. And now there is written information that we know the variance in the population. So the sigma, which is equal to 0.78, milliliters of beer is connected with population of beer bottles. So this is not a sample statistic, yes? Only one sample statistic is your sample mean. Yes, calculated sample mean, which is x with stripe equal to 500.36 milliliters of beer. Yes, so this is sample characteristic. This is a characteristic of this population. Yes, so everything here will be the same as the zero and alternative hypothesis. But instead of student t distribution, we will use normal distribution because variance of the population is known. Yes, so I will write here that sigma or sigma squared is known. Yes, so we will use this test statistic Z, which is calculated like x with stripe minus mu 0 divided by sigma times square root from n. Yes, again we know everything, so we will use our values which we have here. So 500.36. I will write it below, yes, because I don't have enough space. So 500.36 minus 500 as divided by known standard deviation, which is connected with population of beer bottles, 0.78 times square root from 21 bottles. Yes, and the value, I will write it here, this will be value of what? Of test statistic. Yes, value of test statistic. Okay, so please, 0.36 divided by 0.78 times square root from 21. 2.115. 2.115. Yes? So this is value of test statistic. And again, this test statistic Z can be element either of region of acceptance or rejection region. Rejection region for the particular level of significance, yes, alpha. Okay, so which rejection region will be selected now? Again, the third one, yes. So I will delete, for example, these characteristics, yes, and I will write here from your formulas the form of rejection region. W alpha is equal to. So for the Z statistic, yes, is valid if absolute value of your Z test statistic is higher or equal to critical value from the tables Z 1 minus alpha divided by 2, we entered to the rejection region, yes, and zero hypothesis will be rejected, yes. So I will delete this because we need a space. Value of test statistic is written here, so we know that this is our Z value. Yes, I will delete also this, and we know that we are using alpha equal to 0.05, 5% significance level. So Z1 minus 0.05 divided by 2 will be Z 0.975. Do you remember the value of this quantile? As the value of this quantile from the tables, Z 0.975 is 1.96. If you don't believe me, please find statistical tables and verify that I'm not lying to you. 1.96 is critical, so this is critical value. Yes, this is critical value, and this is value of that statistic. And if absolute value of that statistic is higher than this critical quantile, we enter to the rejection region, and at a particular level of significance, we are rejecting zero hypothesis. So what happened? I will delete this, and I will write here a question. Absolute value 2.115. Higher or equal 1.96. And the question is here. It's true, yes? This is true, so we enter to the rejection region, and zero hypothesis is rejected. Zero hypothesis is rejected at the alpha equal to 0.05. It is not equal to 500 milliliters of beer. The mean is different. So the reparation of the filling line for beer bottles was not successful. We will continue with another example about the election. Yes, the limit for election for each political party, one party, yes, in the Czech Republic, into the House of Commons is set at 5%. Yes, if you have one political party and you would like to enter in election to the House of Commons, you need at least 5% of voters. Yes, for the entrance. So there was a survey carried out where from 350 respondents, 28 people voted the monitored party. So we have here some survey, yes, the sample size, the sample of voters, yes, and 28 of them from this sample, yes, would like to vote the monitored party. And there's a question, can we expect that this party will get into the House of Commons in elections with significance level of 1%? In other words, we would like to be sure, yes, with 99% probability, yes, that this political party will or will not enter to the House of Commons. Yes? So how can we solve this? In your formulas, yes, we can scroll down and we can find another table with population proportion, testing of population proportion. Large sample. What is it, large sample? The sample where we have at least 30 observation. Yes. So in our case we have 350 respondents. So we have a large sample. And there is only one test statistic, yes, with distribution normal distribution Z here, and again we have here 1, 0 and 3 types of alternative hypothesis. Yes, you can see the proportion is equal to some value, or the proportion of voters will be higher than some value, proportion of voters will be smaller than some value, yes, and the proportion of voters is not equal to some set value. Yes? So we will select appropriate alternative hypothesis. Test statistic is written here. We will calculate the value of the statistic, and after, on the basis of selected alternative hypothesis, we will select it appropriate rejection region, and we will decide. Yes? So please make ready this table in front of you, and I will solve the rest on the whiteboard. Okay, so according to our example, yes, I will again draw a story on the whiteboard. There is, for example, I don't know, small town, yes, or some population M, yes, and this population is a population of potential voters, yes, and we selected only a sample of voters, yes, 350 in this situation, yes, and you asked these potential voters with a question, yes. There is a political party, and for example, in the case that this will be only one political party on the world, would you like to vote this political party? And you hear the yes in the case of 28 examples, yes, 28 people. So 28 people said, yes, I would like to vote this political party to the House of Commons, yes. So we are able to calculate a proportion, yes, we are able to calculate a proportion of potential voters of this political party, like M divided by N. In our situation, 28 persons who would like to vote this political party, divided by 350, yes, and the result is 28 divided by 350, enter, 0.08. 0.08. What it means, 0.08. It means 8%, yes. And you know that the limit, yes, for each political party to enter the House of Commons is 5%, yes. We have here only small sample, yes, small sample, and from this small sample, 28 people would like to vote this political party. But we require significance level equal to 0.01, 1% significance level. It means that we would like to be sure in 99% probability, yes, that our result, this result, will be connected with the population, that the people from the population will vote the political party, yes? So this is the reason why we are using hypothesis testing. So we will set 0 and alternative hypothesis, yes, and we will test this. So 0 hypothesis is only 1, yes? That is written that P is equal to P0, proportion of voters, yes, who would like to vote the political party is equal to some value. In the Czech Republic, yes, is the limit 5%, so I will set that P is equal to 0.05, 5% of voters, yes, but you will be happy, or your boss, the leader of your political party, will be happy if you reject this hypothesis, yes, and valid will be alternative 1, H1, which claims that proportion of voters who would like to vote the political party will be higher than P0. In our situation, we will be happy if proportion is higher than 0.05. If we reject this hypothesis, at 1% significance level, yes, you can be sure in 99% probability, yes, that proportion of your voters will be higher than 5%, and you will probably enter to the House of Commons. Yes, so this is very important, and we set the zero and alternative hypothesis. Yes, so this is our deal. We will continue with test statistic, which is only one in this situation. Yes, its distribution is standardized normal, and we have written in nominator there is p minus p0 divided by, and we have here square root, where is p0 times 1 minus p0 divided by n. Yes? So we know everything. We have calculated this proportion. We know what is written in zero hypothesis, and we know the sample size, which is equal to 350. So we are able to calculate the value of test statistic. Yes, we are able to calculate the value of test statistic. Z is equal to 0.08 minus 0.05 divided by, and there is square root, where we have 0.05 times 1 minus 0.05 divided by sample size 350 respondents. Yes, so this will be equal to value of that statistic, yes, which will be written here. So please, I will start here. 1 minus 0.05 times 0.05 divided by 350. Square root from this value, and the numerator is 0.03 divided by this result. I have here 2.575575. So this is the value of the test statistic. Yes, so I will delete this because I need a space here, and if you remember the next step, yes, this value of that statistic must be compared with critical value from the tables. Yes, I selected this type of alternative, so I will check the formulas, and it means that I selected first alternative from the formula, so I will select the first version of the rejection region. Yes, there is written W alpha equal to, and there is written for statistic Z, yes, is valid if Z is higher or equal to value from the tables Z1 minus 1 minus alpha, only alpha, yes, because there is only one-sided alternative, yes, there is not non-equal, yes, higher or smaller, so there is only 1 minus alpha. It's different, yes, as the previous example. So, if our test statistic is higher than this critical quantile, zero hypothesis must be rejected at the particular level of significance. So, we are using alpha equal to 0.01, so we must find Z 0.99, 99% quantile from the standard normal distribution. So please check the tables, yes, check the tables and verify to me that you are able to find, wait a second, value 0.99, its value is 2.326. 2.326. Yes, check your statistical tables. Yes, and find p-value 0.990. This p-value, yes, and the result of this quantile is 2.326. And now there is a question: if 2.575 is higher or equal to 2.326. Yes, this is true. Yes, okay, this is true. So we entered to the rejection region W alpha, and zero hypothesis is rejected at the 5% significance level. So your boss, the leader of the political party, can expect, yes, that with 99% probability he or she will enter to the House of Commons with his or her political party. Yes, so we rejected zero hypothesis. Probably we can expect on the basis of our data, yes, that the proportion of voters who will vote your political party will be higher than 5%. We will solve another example. During repeated rolling of the fair dice, yes, there were observed from 60 rolls those results. We have here value xj, yes, which can be observed on the fair dice 1, 2, 3, 4, 5, and 6. Yes, we know that we performed 60 rolls in total. Yes, and we have here empirical absolute frequencies, so observed frequencies observed on the dice. Yes, 9 times we observed value 1, 8 times we observed value 2, etc. 11 times we observed value 6, yes, on this dice. And we would like to verify on 1% level of significance that the fair dice is alright. It means that it has its centroid in the geometrical center. What it means? We know that theoretically, yes, if the dice is alright, I have 60 rolls, so I expect, yes, that 10 times I will see value 1, 10 times I will see value 2, theoretically, yes, 10 times on the dice I will see value 5, 10 times I will see value 6, yes, and I have 60 rolls. So this is my expectation, but the reality is different. Yes, you can see empirical absolute frequencies are different in comparison with values 10, 10, 10, 10, 10, 10. So I would like to verify on 1% level of significance that these values, empirical absolute frequencies, are equal to theoretical expected frequencies, which I expect in the case that the dice is alright. It means that the dice has its centroid in the geometrical center. Yes. So we will use chi-square goodness of fit test. Yes. There you can find chi-square goodness of fit test, where zero hypothesis is written here. There is only one alternative. We need to calculate test statistic G with chi-squared distribution. Yes. Okay, so we will do this. And after, we will compare the value of test statistic G with critical quantile, critical value, yes, from the tables on a particular level of significance, and we will decide, yes. So please make ready these formulas in front of you, and at the end, yes, at the end of this example, again make ready your statistical tables, and it will be necessary, yes, to prepare this table 5, quantiles of the chi-square distribution. Yes, so everything is ready. I will solve this example for you on the whiteboard. Okay, so it's necessary to start at the beginning. So I have here xj, the values, the position on the dice. Yes, 1, 2, 3, 4, 5, and 6. And we have here nj, so empirical values, empirical frequencies, 9, 8, 11 times 12, 9, 11. Yes, so this was written in our example, and now I will set zero and alternative hypothesis. So what's written in the case of zero hypothesis? H0 climbs Pj is equal to P0j. Yes. Alternative hypothesis H1 is non-H0. So what is written here? Relative frequency, relative empirical frequency is equal to theoretical relative frequency, which should be here in this table in the case that the dice is alright, that the dice is independent. Yes. So we know that we have 60 rows in total. Yes. So I expect, yes, I expect that there should be P0j, yes, theoretical relative frequencies. Which one? 10 divided by 60, yes, 10 divided by 60, and here 10 divided by 60, here 10 divided by 60, 10 divided by 60, and here 10 divided by 60. Yes, so there I have a structure, yes, of our theoretical expected relative frequencies. Yes, 10 divided by 60. This is sample size, yes, and 10 times I will expect, yes, this position on the dice, yes. But instead of this, I have here Pj, yes, I have here Pj. So what is a Pj? 9 divided by 60, yes. 8 divided by 60, 11 divided by 60, 12 divided by 60, 9 divided by 60, and 11 divided by 60. Okay, so do you know what is the principle, yes, of this hypothesis test? The principle is that we are testing in 6 cases, yes, in 6 cases, yes, we are testing that this is equal to this is equal to this is equal to this, etc. Yes, so we must evaluate the differences. Why and how I have here a test statistic G. Yes, I have a test statistic G, which is calculated like there is a summation through all j. Yes, summation through all j, and we have here nj minus n times p0j. This is in squares divided by n p0j. Okay, I can rewrite this to form this one. Yes, G is equal to summation through all j, and here nj minus nj with stripe squared divided by nj with stripe. What it means? Empirical absolute frequencies, these frequencies, minus expected theoretical frequencies, which should be here in the case that the dice is alright, yes, squared divided by expected theoretical frequencies. Yes, how can we calculate this nj with stripe or n times p0j? Like n times p0j. Yeah, so for example here n times p0j. So in all cases, in all 6 cases, yes, there will be 60 times 10 divided by 60. Yes, so in all cases here will be 10. Yes, so I know what is it nj with stripe, so we know that nj with stripe is equal to 10. Yes, and we can solve the test statistic. Yes, so please, I will delete this, everything this. At the end, I will write a 0 and alternative hypothesis one more time here, yes, on the whiteboard, and we will calculate the value of G. G is equal to 9 minus 10. This must be in squares divided by 10 plus, and we can continue, 8 minus 10. This must be in squares divided by 10 plus, and we can continue, 11 minus 10. This is in squares divided by 10 plus, and another case, 12 minus 10. This is in squares divided by 10. Yes, I will delete this formula because I already know what I must solve. Yes, plus 9 minus 10. This is in squares divided by 10 plus 11 minus 10. This is in squares divided by 10. Okay, so the value of G will be equal to 1 squared divided by 10 is 0.1 plus 2 squared divided by 10 is 0.4 plus 1 squared divided by 10 is 0.1. Yes, here 2 squared is 4 divided by 10 is 0.4 1 squared divided by 10 is 0.1. And finally here is again 0.1. Okay, so equal sign, and here will be value of g. 1 plus 4 is 5, plus 1 is 6, 1.0, 1.2. 1.2 is the result of g, test statistic g. Yes, so I will delete this and I will return to our formulas because I must rewrite the rejection region. Rejection region W alpha is equal to, for statistic g is valid, if g is higher or equal to critical quantile chi squared 1 minus alpha %. Yes, we enter to the rejection region and we must reject zero hypothesis. Zero hypothesis, yes, will be written here again. H0 climbs Pj is equal to P0j. Yes, so empirical frequencies are equal in all cases to expected theoretical frequencies, relative frequencies, yes, which will be in the table in the case that the dice is independent, yes. So what is necessary for us? We know that we are using 1% significance level, 1% alpha, yes, alpha is equal to 0.01. Therefore, we must find in the tables chi squared quantile 0.99, 99% chi squared quantile with degrees of freedom. Degrees of freedom ni. Yes, please check your formulas and check the statistical tables. Ni is in the first row, yes, and ni is calculated. Please check your formulas. There is written, assuming H0 is true, ni is equal to k minus 1. K minus 1. K minus 1. Yes, are you able to see this? What is it? K, number of rows, number of cases. Yeah, so in our situation, K is 6, minus 1 is 5. So please find in your statistical tables this quantile with 5 degrees of freedom. Yes, 5 degrees of freedom, and I will write the value of this quantile here. Yes, so please do this and compare the value with me. So 5 degrees of freedom, 15.1. Yes, please find 15.1, this critical value in the tables. Yes? Did you find it? I hope that everything is alright. The column 99% in the middle. Yes? 5 degrees of freedom. Ni is equal to 5. Yes? And this is critical value. Okay, so now we can compare this G with this critical quantile. It's not true, yes? G is not higher than 15.1, therefore zero hypothesis is not rejected. Zero hypothesis is not rejected at 1% significance level. It means that this value is equal to 10, this value is equal to 10, this value is equal to 10, etc. It means that the dice, the fair dice, is really fair dice. Yes, it has its centroid in the geometrical center. Yes, so dice is alright. And now one bonus. I will take a chewing gum. Yes, and I will put the chewing gum on one side of this dice. Yes, so for example, I will put the chewing gum on the position 1. 1 will be heavy, and instead of 1, you will see more times value 6. So instead of 9 here will be, for example, value 1, and instead of 11 here will be 19. Yes, so I change something on the dice. Yes, and the dice probably is not alright now, because the dice has a chewing gum on one side, and one side is heavier than the other one. Yes, so what happened here? There will be difference. Yes, and there will be difference. Yes, so there will be 1 minus 10, and there will be 19 minus 10. Yes, and instead of this value here, and instead of this value here, will be other value. So 1 minus 10 squared is 81, yes, divided by 10 is 8.1. Yes, so result here is 8.1. Yes, and also here where we have 19 minus 10 squared is again 81 divided by 10, 8.1. Yes, so we can calculate the new value of G, as the modified value of G, 8.1 plus 0.4 plus 0.1 plus 0.4 plus 0.1 plus 8.1. Yes, and the result, instead of 1.2, is 17.2. Yes, so we can compare 17.2, yes, with critical quantile 15.1. This is higher. Yes, so this inequality in the case of rejection region is true. So now we entered to the rejection region W alpha at 1% significance level, and zero hypothesis H0, which climbed Pj is equal to P0j. Empirical relative frequencies are equal to theoretical expected relative frequencies, which will be in the table in the case that the fair dice, yes, that the fair dice will be independent. Yes, this hypothesis is now rejected at the 1% significance level. Yes, because now there is somewhere a chewing gum on this dice. One side is heavier than another one. Yes, and this distribution is not uniform now. Yes, you have here that we increased the differences, and because the squared differences increased, increased also the value of G, and now value of G is higher than critical value. Therefore, we are in a rejection region, and we must reject the zero hypothesis. So we rejected hypothesis that the dice is fair. It's not fair now. Yes, it's not a fair dice. It's not independent dice. So we rejected something like independence. And now remember this word, independence. Yes, because next week we will continue with hypothesis testing, and we will continue with testing of independence or dependence. Yes, so this is very important now, a very important point, that we rejected, in other words, we rejected independence of the dice. Yes, so that's all. That's all for today. I hope that everything was clear. I hope that I will see you next week on the next seminar, seminar number 12. So this is the end of seminar 11. I wish you nice rest of the day, and I hope that I will see you later. So that's all, and bye-bye.